just to launch it, absolutely natural to have it this day. In this first meeting after Dick Askey left us, spend a day to remember, reminisce, and discuss science with him in mind. The field would not be what it is without him. I can, I'd be curious. I could guess that almost every speaker, in one way or the other, in his or her talk, will have mentioned his name. And he was so benevolent, always being so kind to individual, to all people, enthusiastic about all the applications, and also caring, with the teaching of mathematics. Feel honored that we can have this session, this day dedicated to him. I want to thank Murad Ismail and Howard Cole, who in particular dedicated much attention to setting this day up. And without any further ado, I will pass the command to Murad, and also want to, not before thanking all the speakers that have agreed to contribute and have responded to their call. So Murad, if you would please take us going.
All right. Okay, our next speaker is Kathy Driver from South Africa. She will talk to us about series of polynomial special functions. And Kathy, like all of us, was influenced by Askey. She was not his student or postdoc, but she was, influenced by him through many discussions. Okay, Kathy, I guess you will tell us.
Yes. Can you hear me, Murad?
Yes, yes.
Oh, excellent. I think that listening to Jacob speaking reinforced everything that I'm going to say in my talk today. The influence that Dick Askey had was profound on many of us. And I think that his commitment to the subject surpassed his desire to always be a co-author or whatever. I think he was a simply remarkable man. So I'm going to talk about a few separate situations where Dick had suggestions, and in fact, one of them touches on a paper, Graphs as an Aid to Understanding Special Functions, that Jacob mentioned in his talk. So there will be some overlap in that sense. But to get back to the basics, I first met Dick around 30 years ago at a conference in Granada in Spain. And he attended my talk, which was essentially one of the papers in my PhD on the convergence of simultaneous Hermite-Padé approximants to an n-tuple of Q hypergeometric functions. So it doesn't sound like a neat and easy topic, but immediately after my talk, Dick introduced himself to me, told me he'd read my PhD thesis, which he liked very much, but I should change my notation, which I think was in some sense really very typical of Dick. He had strong views on all of these things. I promised that I would do so, and I sat with Dick when attending the next talk. He was making quite a lot of noise. He appeared to be asleep. And people were smiling and laughing. But as soon as the applause greeted the end of the talk, Dick raised his hand and asked the most pertinent and penetrating question. And I think that was typical of Dick. He knew a lot of things before a person had said them. So Jacobi polynomials were Dick's favorites, and the Jacobi polynomial of degree n is defined by 2f1 hypergeometric function that is a polynomial in X. Much of what I'll say now is well known, so I will go through it fairly quickly. For each value of alpha and beta greater than -1, the sequence is orthogonal on the interval -1, 1 with respect to the weight function 1 minus x to the alpha, 1 plus x to the beta. So this is the usual notation for orthogonality, Pn, Pm, 1 minus x to the alpha, 1 plus x to the beta, integrated from -1 to 1 is 0 for m not equal to n, and it's the L2 norms, non-zero for m equal to n. Another property of the zeros of polynomials in any orthogonal sequence is that the roots or zeros of two polynomials of consecutive degree interlace. The zeros are real, simple, and interlacing, and between each pair of consecutive zeros of Pn, there's exactly 1 zero of Pn minus 1. So this is very well known. For Jacobi polynomials, if you list the zeros, they lie in the interval of orthogonality -1 to 1, and each of the exactly n minus 1 open intervals with endpoints at consecutive zeros of Pn contains exactly 1 zero of Pn minus 1. So it fits exactly, and there are the required number of intervals for full interlacing to occur. At zeros of two polynomials of equal degree, I'm not sure who the first person was to look at this, but the first paper I came across is the one that Jacob also referred to, which was written by Dick. And that is if you take the n real simple zeros in increasing order, x1n up to xnn of Pn, and y1n up to ynn are the n simple zeros of Qn. The zeros are said to be interlacing if you either start with an x, as it were, and then y, x, y, and so on up to x, n, n, y, n, n, or the other way around, start with y1n, then x1n, strict inequalities up to ynn, xnn. And this leads me to the first discussion with Dick. In graphs as an aid to understanding special functions, he proved that take two Jacobi polynomials of equal degree n corresponding to parameters alpha beta and alpha beta plus 1 with the conditions of orthogonality alpha greater than -1, beta greater than -1, those zeros are interlacing. And he conjectured in that paper that you can, in fact, increase the second parameter by 2 and interlacing would still hold. A slightly more general result was proved in a joint paper with Gegenbauer and Buyi, 2009, so big time gap there. But we did show that the zeros of the Jacobi polynomials Pn alpha beta and Pn alpha minus s beta plus t are interlacing, provided s and t both lie between 0 and 2. And this number 2 turns out to be quite significant in many of the discussions that follow. You need alpha minus s to be greater than -1 and beta greater than -1 for the second polynomial to be orthogonal. You need to ensure alpha minus s is greater than -1. And our proofs use mixed three terms recurrence relations that follow from contiguous relations for hypergeometric functions. Quite a powerful tool when dealing with this type of property of the zeros. So when I chatted to Dick at a conference in Irsee, he said, well, what about Laguerre polynomials? We know that for alpha greater than -1, the sequence is orthogonal on the semi-infinite real line, 0, infinity, and the weight function is e to the minus x, x to the alpha. So if you take two Laguerre polynomials of equal degree n and change the parameter from alpha to alpha plus t, in which t interval will you have interlacing? Similarly, consecutive degree n and n minus 1, when do you have interlacing? And the still cheese type problem where the degrees of the polynomials can differ by more than 1. What about ln alpha and ln minus k, alpha plus t? When are those zeros interlacing? What is the t interval that has interlacing holding for every value of n? Very important, every value of n. This other question to me at the time, which I found quite absorbing, is there a sharp t interval? In other words, do we know what the kind of endpoint is for the range of the parameter t? And the second part of the question was, if you've got more space, in other words, you're looking at, say, k equals 2, so you've got the zeros or the roots of ln alpha and ln minus 2 alpha plus t, there's perhaps more space. Is the interval bigger in which interlacing of the zeros still takes place? and it's in the Stilche sense. Of course, there will be gaps because there are not enough roots of ln minus k alpha plus t to fill all of the gaps between the consecutive real zeros of ln alpha. So his question to me was, is there a sharp interval? And if so, does that sharp interval change with k? We did expect it to. In a paper with Kirsten Jordan, we showed that the roots of equal degree Laguerre polynomials are interlacing for 0 lying between t and 2. And we had numerical counterexamples, but certainly no sharpness proof. And also we looked at the Stilche's interlacing question in a 2011 paper, ln plus 1 alpha, ln minus 1 alpha plus t, and we could show again that for these discrete values of t, and I think this is the important point here, that they were interlacing. If the degrees differed by 2, then the zeros or roots were interlacing for t in 1, 2, 3, or 4, but only integer values, so that we could prove using the techniques of using mixed three-term recurrence relations. So again, we had numerical counterexamples for t greater than or equal to 5, but no mathematical epsilon delta type sharpness proof. That waited for Martin Muldoon to get involved in this topic, and interestingly, we didn't prove what I think was probably the simplest of all the cases, the equal degree Laguerre polynomials, but we proved the more difficult ones first. The 2013 paper with Martin Muldoon was that the roots of ln alpha and ln minus k alpha plus t are interlacing if t lies between 0 and 2k inclusive, and this interval is sharp for interlacing to hold for every value of n. In other words, there exists a number n naught such that the roots of ln alpha and ln minus k alpha plus 2k plus epsilon are not interlacing for n greater than n naught. It took us quite a long time, and I'll discuss how we got there. There's a 6-year gap between the so the first one handles k equals 1 as well, so that's the consecutive degree, the 2013 paper. But in 2019, Martin and I managed to prove, looking at Dick's question, that the roots of ln alpha and ln alpha plus t interlace for every n, if and only if t lies between 0 and 2. In other words, there exists a capital N naught, such that the roots, if you increase from ln alpha plus 2 to ln plus 2 plus epsilon, the roots are not interlacing. So the main idea for the proofs of the sharp interval in equal degree Laguerre polynomials in the first work 6 years earlier with Martin Muldoon that Dick had suggested came from looking at connections and inequalities between the roots of Laguerre polynomials and the roots of Bessel functions. And there's a wonderful paper, and that led us to the proof of the equal degree by a Hungarian physicist stroke mathematician, Tamás Pálmai, who showed that the sharp t interval for the interlacing of the roots of Bessel functions, J nu and J nu plus t, is t lying between 0 and 2, including 2. And using his result, we could prove the sharp interval for the interlacing of roots of 2 equal degree Laguerre polynomials. So interesting that what one would think was the more difficult situation turned out from our point of view. We used a lot of roots of Bessel functions and inequalities in a subliminal rather than explicit, well, not subliminal, they were explicit, but we didn't really see the connection in the different degree, the unequal degree papers, until we read Pálmai's paper. 2010, Dick asked me at a conference, if you have different parameters and different degrees, can you say anything about the Stilche's interlacing? So as much interlacing as can take place does, and the Stilche's interlacing holds between the positive, or conversely the negative, roots of the ultraspherical or Gegenbauer polynomials Cn lambda and Cn minus 2 lambda plus t for t lying between 0 and 2, including the values t equals 0 and t equals 2, and fixing k in 0, 1, 2, or 3. If there are no common zeros, we have two symmetric points once the degree difference is 3 that interlace with the zeros of Cn lambda, and zeros occur if they occur at all, and that's not a very well understood topic when two different degree, different parameter orthogonal polynomials can have common zeros. There's a paper by Gibson, but not many results on that issue. They occur at two symmetric points that we identified, and since the interlacing argument shows that common zeros cannot occur at the largest zero, these extra points give good lower bounds for the largest zero. And now I'm going to come to my third story about Richard Askey making suggestions, as he always did. He always made time for me at conferences to discuss what I was working on and give me ideas. I have several pieces of paper scribbled, but I don't have photographs of them, as Jacob did in the previous talk, unfortunately. But this was perhaps the crowning glory, and I've left it until last. Peter Borwein and Chen wrote a paper on the asymptotic zero distribution as n goes to infinity of a particular integral. Integral 0 to 1 t to the k, 1 minus t to the s, f z of t, the whole expression, the integrand is raised to the power n, where f z of t is polynomial in t and analytic in z. Duren and I were interested in the asymptotic behavior of the roots of the hypergeometric polynomial 2f1 minus n, n plus 1, 2n plus 2z, and you'll notice that the denominator parameter there, 2n plus 2, is twice the second numerator parameter, so that's not an accident. And using the Euler integral representation and some simple properties satisfied by gamma functions and beta functions, we expected the roots of this expression asymptotically to approach an arc of the circle. So this was simply using the Borwein-Chen results. And what we found, to our absolute alarm, it was a total crisis, I remember, that the plots showed that for each value of n, didn't matter how small, the zeros actually lie on a specific arc of the circle, center 1 and radius 1, with the real part of z greater than a half. So it was not an asymptotic result. It was true for every n. And so at the conference in Mount Holyoke, Peter Duren and I told Dick that we'd used this result of Borwein and Chen, and that for each n we had found that zeros of this hypergeometric polynomial 2f1 minus n, n plus 1, 2n plus 2 lay on the circle, center 1, 1, 0 obviously, and radius 1. And we had seen that for the parameter didn't need to be related to n, it could be b to b, which is the same pattern, but slightly more general, of course. And for each b greater than minus a half, the roots of that 2f1 lay on the circle. So Peter Duren and I walked up to Dick. It was at the cocktail party of this conference in Mount Holyoke, and we said, we've observed this phenomenon with the Borwein-Chen paper, and it should be an asymptotic result. So you want to see that nice picture of the zeros getting closer and closer to the curve, but in fact we found that they lay on the curve. And he said, do you have a pen and a piece of paper? And he wrote down this equation linking the hypergeometric polynomial 2f1 minus n b2b, 1 minus e to the I2 theta, with the ultraspherical polynomial. So Peter and I were absolutely standing there with our mouths open. Dick got it in one minute. And what we could show was, of course, that because the ultraspherical polynomials, the sequence is orthogonal on -1, 1, we know the weight function. For b greater than minus a half, the zeros lie in -1, 1, and using the connections between the ultraspherical polynomial and the hypergeometric 2f1, we could show that we had this connection. And lambda, you'll notice that this parameter here is lambda, but I've got b's everywhere else. And what is the connection between them? And that is that lambda is a half minus b minus n. So b greater than minus a half is equivalent in that sense to lambda being less than 1 minus n. This was the connection between the ultrasphericals and the 2f1 hypergeometric polynomial. The one parameter for the ultraspherical being lambda, and the parameter for the 2f1 being b, and the connection between them depending on n. It's a half minus b minus n. So we have that if one replaces w, put w equal to 1 minus z and do the simple arithmetic involved, we found that this expression brought us back to the ultraspherical polynomial, and that told us that when b is greater than minus a half, the roots of the ultraspherical polynomial will satisfy the 2f1s lie on the circle center 1, radius 1, so we get the same thing there. And that simplifies to tell us that the roots lie on the imaginary axis. So the set of points satisfying this equality here lie on the imaginary axis. The pseudo-ultraspherical polynomials, which are a specialty of Murad, in which he's done such seminal and wonderful work. If we look at the pseudo-ultraspherical polynomials defined in this way, we know that for lambda less than 1 minus n, all the roots of the pseudo-ultraspherical polynomial are real. And for lambda less than minus n, the finite sequence where n obviously depends on lambda, and n, if you look at the connection here, lambda less than 1 minus n, that will give us a finite sequence here. One of the things that is interesting is that this discrepancy minus n and 1 minus n is partly explained by the movement of the zeros according to the Hilbert-Klein formulas for the Jacobi polynomials, but perhaps that's a discussion for a different day. So you'll notice that this is lambda less than 1 minus n. We know that the roots are real, but for lambda less than minus n, slightly more restricted, we have this finite orthogonal sequence. In 2013, Martin Muldoon and I proved some monotonicity properties of the real roots of pseudo-ultraspherical polynomials and identified subintervals of the real line containing all the roots. They depend on n and on lambda. And we could show that the roots of the pseudo-ultraspherical polynomial line minus 1, 1, provided lambda obeys that inequality involving n. Just to give a small selection of the papers that were inspired by or sort of indirectly suggested, I mean, can one say inspired when Dick gave us the connection and essentially told me and Peter Duren what to do, but refused, as always, to have his name on the paper. We of course said you must join us as a co-author, but Dick said no. So this is just a small selection from my perspective of papers that were inspired by Dick. The paper with Peter Duren, then a second paper, which was actually quite a lot more interesting. This involves zeros on Cassini curves with Manfred Moller, a colleague of mine at WITS. We wrote a paper on f minus n b minus 2n. The paper with Peter Duren that followed was to discuss the case not where b is greater than minus a half, but the trajectories of the zeros as b drops below minus a half, how the roots of this 2f1 pair off and what the trajectories of those zeros are. The paper with Manfred Moller talked about quadratic and cubic transformations. And of course, the paper I've referred to that Dick inspired was the Jacobi polynomials in numerical algorithms. That was the result that Martin Muldoon and I extended later. the Stieltjes interlacing of zeros of Laguerre polynomials from different sequences. So this is a joint paper with Kirsten. We only knew the integer changes, but that was published. The paper of mine on the ultraspherical or Gegenbauer polynomials, but perhaps the two great highlights were common and interlacing zeros of families of Laguerre polynomials with Martin Muldoon, where we proved the sharp parameter intervals for consecutive degree, equal degree, and the Stieltjes situation with very unequal degree. What I would say very much echoes what Jacob said about Dick earlier. He always made time for me at conferences to discuss whatever topic I was thinking about at that time. He always had suggestions and ideas and about techniques and solutions. It was certainly a great privilege to know him and to spend time with him at conferences. And thank you to the organizers, and thank you for your attention.
Thank you. Thank you very much. Maybe I'll just make one comment before seeing if there are any other questions or comments. Dick didn't, he appreciated the symbolic algebra packages and programs and so on, but he actually never learned how to use them.
Yes.
And he was very influential in the development, and he encouraged it and so on. He knew that this is the way to go. And what's amazing is all these conjectures that are based on graphs and so on.
Yes.
He had them based from very primitive pictures. I mean, the graphs
Yes.
that I'm sure many other people looked at them, but didn't see what he saw.
Yes. Yes.
So he had this insight that, he looks at something that looks ordinary, but he always finds something extraordinary in it. And
yes.
This was just really amazing.
Yeah, but Murad, honestly, that I'll never forget that moment standing with Peter Duren when he said, do you have a piece of paper and a pencil? And he wrote down the connection of what we were looking at with the ultraspherical polynomials. It was just traffic stopping. I mean, we didn't know what to say. He had such an insight into all of these things. And of course, we offered him joint authorship. I mean, he got the connection. He had the idea.
Oh, but, I had the same problem.
Yeah.
Oh, I used many of his ideas, and he wouldn't get his names in the papers. So.
No. So I think 5 of my papers have got a mention, a thank you at the end of the paper to Dick Askey for his very insightful ideas and suggestions. He really was the most remarkable man.
Okay, any other questions or comments?
Can you go back on the references for me to write them?
That was the beginning, I think. No, yes, that's the first one. I can certainly send them to you. Please just send me an email. It's kathy.driver@uct.ac.za, and I can send you copies of any of these papers.
Okay, any other comments?
Yes, Katie, you have results about interlacing for Jacobi polynomials and for Laguerre polynomials, but there is a limit from Jacobi to Laguerre, and does that help to get results for Laguerre from results for Jacobi?
Yes, but absolutely. But to go in the opposite direction, Tom, the interesting thing is that we have sharp results for Laguerre. Everybody knows also what the sharp interval for interlacing of equal degree Jacobi polynomials is. Everybody knows what it is from numerical considerations, but there's no analytic proof yet, as far as I know. I haven't seen one anywhere. So, again, the electrostatic problem, the position of the zeros of the Jacobi polynomials in -1, 1. So that is also well understood, but I don't think there is a sharp proof that for the interlacing property of 2 equal degree Jacobi when you change both parameters but keep them in the orthogonal range.
Yeah, okay. But as you told in your lecture in the 90s, you started with interlacing for Jacobi, and then you moved to Laguerre. So did it help you with obtaining or conjecturing Laguerre results that there is that limit from Jacobi to Laguerre?
Yes, certainly that was used. The other thing that's not really, I'm not really answering your question, Tom, but one of the interesting things is Laguerre, in some sort of vague non-mathematical sense, there is more space because it's a semi-infinite half line that the zeros have to move in. So with Jacobi being -1, 1, perhaps the constraint of the finite interval of length 2 means that the Laguerre situation was easier to prove. I don't know how to prove the sharp result for Jacobi polynomials, to answer your question. Yeah. Using the limit relation, I don't know that will do it, but certainly I'll look at it again.
I show two fingers because I have two questions or two comments.
Okay.
Which Borwein? Very simple. I can think of 3 of them. Okay.
I'm sorry. I apologize. I had Peter Borwein and then I couldn't fit it on my slide. Quite correct, Paul. Peter Borwein and Borwein Chen.
Peter's obituary in Journal of Approximation Theory is essentially ready.
Yes.
Eventually published. It takes time because unfortunately the guy who wrote it, Tamás, is quite ill. Tamás Erdeli.
Yes.
And you know, the other sad thing is that 3 Borweins died within a very short period of time. Yes. And in the wrong order, you know, because the dad survived both sons.
Yes, Jonathan, I think, yes. I mean, they were such wonderful mathematicians. Yes, very, very sad, Paul. Thank you, yes.
Mm-hmm. And my other thing is related not to your talk, Kathy, but it took me time to digest what I wanted to say regarding the Favart theorem in the previous talk. I remember there was a controversy. And then I was thinking, and during your talk, I went to my bookcase, which is right there. I mean, one of my bookcases, the approximation theory bookcase. And I don't know if you guys can see it. This is the book by Nathanson about constructive function theory, volume 2. It has Favart's theorem in it. And volume 2 has a footnote, which I'm going to read to you.
Okay.
So, Favart's theorem. This book was written by I.P. Nathanson, and the footnote talks about I.P. Nathanson in third person, which is already weird, of course, you know. Only kings, I guess, talk about themselves in third person. Anyway, this theorem was also discovered independently of Favart by the author, Nathanson, in the year of 1935, and was presented by him in a seminar led by S.N. Bernstein. He then did not publish the results since the work of Favart had appeared in the meantime. There it goes.
Interesting.
I wonder if Nathanson ever found out that actually neither of them discovered this theorem. That's another issue. I personally never met Nathanson because I think he died maybe a year before I ended up in Leningrad, but I was a student of his son. It was called, those of you who speak Russian will understand it. His name was not Nathanson, but Nathansin. The word sin means son in Russian. Nathansin. All right. For disturbing the peace.
Okay. Any other questions? Actually, there is one more comment about Favart's theorem. Shohat also had the theorem, but he didn't know that it wasn't new, and he proved the paper. He has a paper where he proved not the positivity condition, but if the coefficient is not 0, and there is a signed weight function or a signed measure. And in his paper, he says that he knew about Favart's theorem and somehow Favart published it before him. But he had the more general one, which is for signed measures, not necessarily positive measures. Okay. Any other questions or yes?
I just wanted to add something, but I can't find it right now. I do own a book in Russian, which was from the library, personal library of Shohat, which was annotated by Shohat and talks about Seger's theorem, this and that. But eventually, if I find that book here, then I will show it later. It's very interesting that I have no idea how I ended up in that book. Maybe somebody will help me out. Okay, I shut up now. Sorry.
Yeah.
Thank you.
Yeah.
Any other comments?
Yeah, I have also a remark about that Favart theorem. This is the paper by Meixner in the early 30s, where he introduces the Meixner polynomials. And there he also formulates this Favart theorem. And he has a reference to the book by Perron.
Yeah.
Is this the same paper where he characterized the the orthogonal polynomials in a certain class, or it's a different paper?
The Sheffer polynomials, in a sense, he also introduced.
Yeah, right.
Yeah.
Okay, so it's the same paper. Okay.
Yeah.
Any other questions or comments? Okay, if not, we'll stop. I don't remember the schedule well. So is Luc Vinet in the audience, or Howard? When do we start?
At 5 o'clock Dutch time.
10:45, Professor Ismail. 5.
10:45. Okay.
All right.
All right. So okay. So we'll take a break until 10:45, and we'll see you there. Okay. Thank you.
Thank you.
all.